Okay, so good morning, everyone. Welcome to another webinar of the Netpore project within the construction. And today's speaker is Aitor Lopeandia, who is an associate professor of applied physics at the physics department of the Autonomous University in Barcelona, and a senior researcher at ICN2, which is the Catalan Institute for Nanoscience and Nanotechnology. And after his PhD in material science, he moved to several universities with several fellowships. And in 2010, he returned to Barcelona, where he became a lecturer, and then he became the coordinator of the Master of Advanced Nanoscience and Nanotechnology, and currently is the coordinator of the PhD program in physics at UAB. And his research interest revolves around thermal properties of nanoscale materials and their application in energy, so with various interests. And today's webinar title is Measurement of Thermal Conductivity of Zinc Oxide Coated Nanowires using 4-probe thermal conductivity method with AC measurement. So thank you, Aitor, for accepting our invitation, and thank you for giving this seminar. Thank you.
Thank you, Eleonora. Thank you. Yeah, sure. This is the title. I'm glad to be here and to speak about some of the research that we are doing. Of course, this webinar will be around one work that we started a few years ago together with several collaborators, with Luca and others. That let me go. The list is quite long, and there are different people from the Institut Catalan of Nanoscience and Nanotechnology, also from the Institut de Microelectrònica Barcelona, that they help us in the fabrication. Of course, from the INRI, from the Istituto Nazionale di Ricerca Metrologica de Torino. And in the last moment, we have joined some mathematicians from the ETH from Zurich in order to solve some of the questions that we still have to improve. As Eleonora was telling, my research is around the development of techniques and methods in order to measure thermal properties of nanoscale materials, and we have been working quite a lot during last, I would say, more than 25 years already, about heat capacity of nanoscale materials, about thermal conductivity of ultra-thin films, of nanowires, and of course about the applications in thermoelectricity of some of these devices of some of these materials that we do characterize. I wanted to say that in the focus of the presentation, in the scope of the presentation, I will try to focus on the development of the high accurate technique that we have developed in order to measure nanowires, individual nanowires. In that case, the thermal properties, the thermal conductance, the thermal conductivity at the end. And I will show some measurements on zinc oxide coated silicon nanowires, porous silicon nanowires. This is important word that I forget to put on the title. It's a porous material. It's a silicon porous material, and this network is a network about porous semiconductors and oxides. Then it's an important point to point out that this is a porous silicon nanowire. This silicon nanowire, I wanted to start with 5 minutes out of the main topic of the presentation. No, this zinc oxide coated silicon nanowire, porous silicon nanowire, exhibit quite promising thermoelectric properties. I'm pretty sure that most of you are already familiar with thermoelectrical properties, but this is a porous material with quite promising thermoelectrical properties. I wanted to spend a couple of seconds on reminding that the thermoelectricity is a physical phenomena that permits us to pass from waste heat, I would say, where we can promote a heat flux, and from a heat flux we obtain a useful electricity, a useful energy. We can recover, we can harvest energy. This is the generation path. Or either we can use useful electricity, useful energy, useful electrical fields in order to promote, to generate heat fluxes, and then to pump energy from one side to the other of the material. In general, okay, this is quite old phenomena that has been very how to say has been on the on the bad work, no, of the research, because of this phenomenon is very how to say small, and that has very few applications. But among these very few applications, the people has tried to develop thermoelectric generators that compare with conventional heat thermal machines. The efficiency is very poor. No, we cannot compare the efficiency of thermoelectric nowadays, no, with the performances of the materials, essentially because the performance that is typically linked, no, we can speak about the performance of the material through the figure of merit, the ZT. This figure of merit is permits efficiencies quite low, no, but even though no, that this type of thermal machines are quite simple, no, that permit this simplicity helps to scale down them. And the main point is the simplicity. As you can see here, this is a typical Peltier cell, no, with an N leg and a P leg. They connected in series, and we have the two heat sources in parallel. The simplicity is so big that we have no mobile parts, and then reliability of this device is quite large, and the scalability also permits portability, and essentially the reliability has driven some applications like aerospatial applications, like the radioisotope thermoelectric generators that the NASA was how to say mounting on the Voyager or the Cassini proofs. No, the point is that if we think on applying this type of on taking the profit of this scalability, and thinking on the application of on at the chip level, no, there has been traditionally a lack of good thermoelectric performing materials, no, and essentially it's the most compatible, no, because most of the good performing thermoelectric materials are far to be CMOS, no, are far to be compatible with how to say the industrial methods that are used in the microelectronics. No, I would say that there was a window open, no, at the 2008. I would say that we discovered that the low-dimensional silicon nanostructure. This is a couple of Nature articles that they went together into the publication. No. The one by Osbam and collaborators, and the other one by Bukai, and in both of them they proved that the reduction of size, no, the nanowires, the nanowires may exhibit ZTs. It means the figure of merit may enhance several orders up to they claim up to 100 times better than the bulk silicon. No? And it was essentially due to let me go back to the fact that the thermal conductivity was extremely reduced by the fact that the critical parameter in the nanowires, or the characteristic parameters, the diameter of the nanowires, was in the same order of the mean-free path, or maybe smaller than the mean-free path of the phonons, and the thermal conductivity was highly reduced. No, I would say that if we pay into attention, if we go to the Oxfam article, we can see that, of course, they were measuring the thermal conductivity through suspended structures that I will go in detail during the seminar. But the first point I wanted to note is that if you look at the wires, now the BLS, the vapor liquid solid nanowires, the ones that were taken from the coexistence, no? And these nanowires are used to grow with a very flat surfaces, no. And even though they have a reduction on the thermal conductivity, the reduction at 300 Kelvin, no, 300 Kelvin for 150 nanowires was around 40 watts. No, we got a reduction, a factor. No, bulk silicon used to have around 140 watts meter Kelvin. Then with nanowires, we got a reduction of a factor of 4, more or less. No, a bit less maybe. But the fact is that if instead using BLS, they were showing also measurements on electron-less etching nanowires, that they had a huge high surface roughness, And they saw the depression on the thermal conductivity of a factor, in that case, a factor of 6 again. No, then we have already a 25 factor, no, because this 115 the nanowires with 115 nanometers of diameter, they had a thermal conductivity of around 7 watts per Kelvin. It means that the roughness on the surface had a huge effect, no, and that was, I would say, this is a work that we did with together with Luca in the past, and we saw that if we use porous materials, in that case, where the surface roughness and the surface roughness within the volume, no, here you have an axial tomography of the nanowire, and here, even though you cannot see it, there is a little nanowire hanging in between a couple of platforms, of sensing platforms. We got thermal conductivities of around 0.75 watts per Kelvin, what means that it's even 10 times smaller than the thermal conductivity that we got with that electroless etching, no, with MATHE, this metallic assisted chemical etching that they typically used in order to produce porous silicon nanowires. That pointed that these nanowires may be a good candidates to be used as thermoelectric materials. And the point is that there has been some studies recently, where they show, in fact, that with nanowires that were doped with 10 to the 20 more or less, they got already figures of merit of 0.7. That is a quite competitive figure of merit for a silicon base material. No, this is a porous of 46% more or less. No, then this is really promising material, and we wanted in that study that I will present, we wanted to study the case of zinc oxide ALD, atomic layer deposited, of these porous nanowires. We try to deposit. We process. I will not enter too much into detail because I'm far to be expert on the fabrication process of the nanowires. But they use the seeds. This is the seeds, and they reduce the seeds of the nanowires. They do this is not nanowire, this is polystyrene, and they do the position of metal, and then they do the etching, and the etching is preferential below the metal, letting the nanowires on top. And these nanowires, while they have some residual gold in between, and that enters into generating holes. And then the idea was, once we have the nanowires, the forest of nanowires, we can cover them with zinc oxide. Zinc oxide ALD is a conformal deposition technique, and then it will go inside. This is not gold. This is zinc oxide. Sorry, I use a very bad color that I just realized. This is zinc oxide going inside of the porous and trying to fill as much as possible, the porous materials. The idea was, if we are able to deposit a very thin layer of zinc oxide is conductive, and we can increase the electrical conductivity while preserving, because this will be well below the nanometer thickness, the thickness of ALD zinc oxide. We will be able to preserve the low thermal conductivity. We expect to preserve the low thermal conductivity of these wires. Okay, that was the idea. And then as I said, we already had some platforms that this is what we call the traditional suspended platforms, where we have two meanders. This is a 20 per 20 more or less platform with that is separated a few microns one to each other, and we hang the wire in between them. We attach it, as I will show some pictures later, with a focus ion beam. We do the position of the platinum, of the polymeric based platinum, and we hang the nanowire in between them. And then the idea is that if we are able, the platforms are slightly coupled, thermal coupled to the silicon frame, to the bulk silicon frame, and we can thermally actuate through the coils, or through the resistive coils, we can thermally actuate and heat up one platform and then do measurement of the temperature rise of the other platforms and then do the estimation of the thermal conductance. I will not enter too much into detail because of the question, but it's pretty simple. You can solve the heat transfer equation, and we can extract through the temperature rises, we can extract the thermal conductance of the sample of the nanowire. That technique has a limitation that we wanted to overcome. That limitation, in fact, it has two limitations. I said one, but it has two. One is that if we have a highly conductive sample, as you can see here in the picture, no, and we attach the nanowire into the two borders of the platforms. If we have a highly conductive platform and we do measure the temperature profile within the 20 square microns of the platform, here I do, this is a finite element modeling of the temperature profile. If we do a cross section, if we do a temperature along this line, no, we will measure the temperature in the platform, in the wire, and in the other platform. The black curve is the one without a silicon plate, without a diffusive plate underneath. The first problem that we find is that we have a depression of the temperature in the point of contact of the nanowire. It essentially means that we do measure an average temperature in the coil, but we do have the wire with a different temperature in the contact. Then, okay, we can just access to the average temperature. This is a major problem, no? Because we do not measure the real temperature drop in the sample. And at the end, if we want to measure thermal conductivity, we need to get the temperature drop in the sample that we are measuring. And there is a second intrinsic problem that we cannot, this can be, how to say, slightly soft if we just introduce a highly conductive material underneath the platforms in order to homogenize, to increase the heat diffusion within the platforms. And this is with 100 nanometer silicon, monocrystalline silicon plate under the platform, where we can more or less reduce that effect, no? The temperature drop. This is the scale in temperature. The temperature drop and the average temperature in the red line in the platform is more or less the same one that we got on the point. But okay, it's not exactly the one, but it could be more or less considered, no? Because the error will be smaller. But there is a second problem, a second limitation that has to see with the thermal contact resistance. No, we have the similar materials. We have silicon nitride. We have the nanowire in between, and we do the contact with the metallic polymeric based metallic material, and we will have the heat will flow through silicon nitride towards the metal, towards the nanowires, and come back, no, from one side to the other. And of course, as we have different materials with different photon densities, we will have a TBR, we will have a thermal boundary resistance, and we will have a temperature drop between the different materials that could be significant. And could be significant means that in previous measurements, I come back for a while, no, in these measurements, we had a very low thermal conductive materials. No? The thermal resistance of these materials was huge. It essentially means that in these materials, in these nanowires, the most of the temperature drop was dropping on the nanowire. It essentially means that this effect is minimal in this material. But what happens if we have a highly conductive material? It may happen that this temperature drop that we have due to the TBR, due to the thermal contact, could be higher than the temperature drop that we have within the material. Then the uncertainty, and this project was initially thought as a metrological project, no, this uncertainty is a dominant one, no, in highly conductive materials. Luckily, in 2015, Lishi was okay. He came again with a very nice structure. This structure that is based in 4 wires, four parallel proofs that can be heated or sensed independently. Then we have four lines. No, each of these lines is a metallic line. sorry, it's a silicon nitride line that is equipped with a metallic actuator, with a resistive actuator that can be heated up. Now, if we heat up, we have this kind of parabolic profile. Now, this is a console modeling of one line that has been heated with a nanowire in the middle. And the typical profile that we got in a line that is simply sensed is this triangular shape. That is, if we hit the phase, we will be able to measure the temperature drop. If we hit the phase, this is the phase, the number 1, number 2, number 3, number 4. If we hit the phase line, we will be able to measure the temperature in the 3 other lines. No, the resistive measurement will give us the average temperature measurement, but we can extrapolate the temperature in the point contact easily because of it can be analytically solved, that equation. In fact, what we have here, and I do transfer, this is the heat transfer equivalent. No, here we have different resistance, the resistance of the beam, no, from the wire, from the central point to the frame, to the silicon frame, we have the thermal resistance, and we have the thermal contact resistance also, no, and then we have the thermal resistance of this of the piece of nanowire between the beam 1 and the beam 2. The thermal resistance of the piece of nanowire between the beam 2 and the beam 3, that is R2, and the piece of nanowire that will be represented by R3. The fact is, from here we will extract 16 measurements and 16 equations. In fact, this is just Kirchhoff equations. We can treat it as Kirchhoff equations, and we can extrapolate directly the G2, just getting rid of the thermal contact resistance. This is a very clever configuration that Lishi was arriving with, and was arriving with, and this permits us to calculate, or just to remove the thermal contact resistance, and to consider that they will be there. No, this, I say 16 measurements because we do measure the wire that is heated up, and we do measure the 3 other wires. No, we have 4 measurements when we hit the wire 1, but we can, and we have to hit the wire 2 and measure the other 3, to hit the wire 3 and measure the other 3, and to hit the wire 4 and measure the other 3. Okay, from the previous expression, of course, we can derive the associated uncertainty and determine which will be the better parameters in terms of geometry of the suspended structure of the suspended beams, depending on the thermal conductance of our nanowires. Our nanowires will be ranging between, I would say, 10 and 100 nanowatts per Kelvin, and we just how to say, calculate, depending on, this is the thermal conductance of the beams, depending on the length and the shape and the width and so on, the thickness of silicon nitride. We decided which was the perfect structure in order to measure in that range. No? And this is just taking into account the uncertainty, if we are able to determine the temperature in the heated lines the heated line with 5 millikelvin. Sorry, this is correct. Yeah, heated line with 20 millikelvin per square root of Hertz during the measurement, no, and with a measurement of 1 second, consider that we are able to determine the temperature of the measuring lines with breaches and Wisdom breaches and differential measurements of 5 millikelvin. No, then taking into account that, we did a modeling, we did a design, and we fabricate that design. The design, okay, just consider that this is the fabrication process, the fabrication procedure. I will go really fast. If you have questions, I could go in detail later. We start with a silicon wafer. We just do a thermal oxidation and a low pressure chemical vapor deposition of silicon nitride, of a low stress silicon nitride. Then we do the patterning of metal lines, and we do the reactive ion etching of the beams, defining the beams considering the metal lines. Then we cover everything with silicon nitride in order to passivate the lines with 50 nanometers, very thin silicon nitride in the step E. And then we cover everything with LTO, with low thermal oxide silicon dioxide, that is essentially to protect the upper layer, in the final steps. No, in the backside here, as you have seen, we put aluminum mask in order to be able to do debris in the G step. And we stop without breaking the membrane. We stop in the silicon dioxide, and we finally liberate everything with I would say HF immersion and ultracritic drying. In order to liberate that structure that you can see here, that are beams of around 1.5 microns width, with a thickness of 450 nanometers, and that are 400 microns length. These structures are very similar to the ones that were defined by Li Shi. Maybe there is some difference in terms of geometry, but the main difference of our approach that is we will use high frequency excitations in order to mimic the DC approach. If we do hit the system with an AC current, typically we release power at 2 omega. We heat up with a sinus, with a sinusoidal, in the fundamental frequency. We heat up the system at 2 omega, and typically we have a temperature oscillation of 2 omega. But this temperature oscillation is damped by the heat capacity of the system. The temperature oscillation, of course, can be also explored in the resistance. And here we have the DC component, but plus the 2 omega component, and exactly the same with the voltage. That we will make it to appear a 3 omega component that is essentially the link between the current at 1 omega plus the resistance at 2 omega. We can remove that. We can minimize the 3 omega component if we do play well over the thermal transient of the device. The thermal transient of the device, in that case, it was around 20 hertz. And we typically do the measurements at 600 hertz. It essentially means that this 3 omega is right here. This 3 omega voltage is almost negligible. It essentially means that our systems electrically will have the AC component, but thermally we will behave as a DC system. Through that strategy, we can, with using that dynamic methods, we can highly reduce the noise, using noise rejection locking amplifiers strategies. And we typically got values, signal to noise ratios determining the resistance of around 10 to the 5. 10 to the 5 means that the uncertainty, the magnitude over the uncertainty is around 10 to the 5. Of course, if you have that type of sensitivity, you require also to have a system with similar sensitivity. And in that case, we use an helium cryostat. In that case, that we have changed the control setup. We just skip the commercial one, and we develop a PC-based temperature control, PID control, with high resolution sources in order to get the stabilities of around 1 Kelvin, 1 millikelvin, sorry. 1 Kelvin, no. 1 Kelvin, we could not measure anything. Then this is the electronic chain. We have one line that we can heat up with a 62. It's a Kidley 6221. It's an AC current source that we can heat up one of the lines, and we can do measurement in another line that is heated up with another Kidley. In that case, it's not the Agilent that I show here. It's another Kidley 6221. In one, we will do a staircase of currents going from, in that case, is around 5 microamps to maybe 20 microamps or 30 microamps at the end. And here we keep a constant amplitude of around 5 microamps. The fact is we could measure the temperatures in both cases, The holder temperature stability, as I said, is around 1 to millikelvin, and we can see here the resolution. If we do not have a correct oscillation, as you can see here, the drift of this resistance is because of the temperature holder, not because of the resolution of the 1 omega signature. In order to be able to measure up to 4 channels in parallel, we have developed an FPGA-based locking amplifier that can be can be easily scale up, no, in order to have several measurements in parallel. What is the measurement? The initial measurement that we have to do is just we need to calibrate the temperature coefficient of resistance, and for that reason we do the staircase. We can extrapolate the temperature, the resistance here. Now we do the staircase of currents. We do measure the different resistance for each one of the amplitudes, and we can extrapolate the resistance at zero heating, I would say, without self-heating. And this R0 can be plotted as a function of temperature, and that permits us to calibrate as a function of temperature the variation of resistance. So we can extrapolate. This is the first. The second point is, of course, that if we take into account the calibration of the resistance, we can measure the thermal conductance of the beam directly, no? through the slope of the curve we obtain plotting resistance as a function of E square. Once we have done that, the first calibration, the first check that we have to take into account, which is the cross-talking, not through conduction, because we will do the experiment, we will complete the experiment in ultra-high vacuum, which is the cross-talking by radiation, no? Because we have around 400 microns beam that is around a couple of microns close to another beam, no? And if we do the checking here, we are heating up the line one, this one, up to values. This is 15 Kelvin, is more than 3 times the temperature drop, the temperature rise that we promote in the final experiment. It means we are well over, no, because radiation will not be linear, will be in that case cubic, and we can check which is the rise in temperature in the parallel line. Here we can have this one, and we saw that we have an increase of around 110 millikelvin, and if we do translate that into thermal conductance, we can see that the thermal conductance is around 1.34 for 15 Kelvin delta T. No, it's around 15 Kelvin delta T. We're injecting the same power in all of them, but of course, because of the beams are, how to say, they ideally are equal, but in some cases there are some divergences, no, in the shape in the final microfabrication. We could check that even in the WAS situation, now heating up 3 times the temperature that we use in the experiment. In the experiment we used to use around 5 Kelvin. We got a thermal conductance link of around 1.3, 1.4 as maximum nanowatts per Kelvin. It's a very small thermal conductance. No? And of course, this is in the beams are not, the distance between the beams is not homogeneous. The two in the limits are more or less the same. No, in the center we have around 3 microns, 3, 4, 5 microns, and depending on the design, and we have much smaller. No, this is the value that we have to take into account. No, the thermal conductance between the beam 2 and the beam 3. Okay, once we have characterized, we have fabricated the device, we have characterized the device, we send it, we typically send it to INRIM, no, to Eleonora, to Luca, and in the focus ion beam that they have, the scanning electron microscope that they have equipped with a microfabricator, with a nano manipulator, and a focus ion beam. They used to selectively place in the center of the beams a nanowire. This is a very tricky step, and how to say, sometimes quite time consuming, no, because they have to go with patient. No, they took this is the point, the point of the nano manipulator, and here we have the nanowire. I don't see if it could be easily seen. And then we do deposit with the focus ion beam. We selectively deposit platinum on the contacts. No, this is the typical contact that is around, okay, we have a nanowire here that is around 250 nanometers of diameter. Then we have here that is around 50 nanometers wide, the contact, you know? And we contact in the 4 beams. And then we have the sample prepared to do the final measurement. No, if we take into account here, we can do the of course, if we want to take the thermal conductivity, of course, we need to take the dimensions from the nanowire. And here we have the diameter that was around 250 nanometers, and the length. The length, we can determine the length with a quite good precision, but for the diameter, well, we have maybe the uncertainty is the dominant one, no, in the final measurement, no, because here to determine the real diameter of the nanowire, considering the contrast and everything, is quite difficult, no? And we can consider that we have around 10% of uncertainty in that measurement. That is not that much. If we do the first measurement, just considering that we are heating up the first nanowire, we will heat it up introducing very few power. No, it's around 10 to the minus 7 is 600 nanowatts. 600 nanowatts, and we heat it up around, as I said, around 4 to 5 Kelvin. No, it's 3 times less than the experiment that we did in order to check the cross-talking, the radiation cross-talking. We can see the temperature rise, of course, in the next wire, in the wire 2, we got 0.393 Kelvin. In the next, of course, it dropped, no, and we have only 123 millikelvin, and in the last we have around 65 millikelvin. That's the reason, in fact, that small movement of the last wire is the reason why we need such a good thermal stability of the temperature bath. This is the stability of the temperature bath, and this is 2 consecutive measurements, one in red and the other in black, and the following in black. No? And this is the stability that we got during the measurement. That is, in all the cases, well below or around 2 millikelvin. Then we can do the 16 measurement, because here I'm just showing the measurement for when we hit the beam 1, but we can do the rest of the measurements, and we can just fill the table. Of course, we will get all the measurements, and here you have all the different tables. No, when we hit the beam 1, 2, 3, or 4, and we sense the rest of the beams. No. And taking that values and solving the heat equations, we can go. And here we have to do an approximation, no? Because in order to solve the complete equation with all the RCs and RBs, and considering that the determination of RCs and RBs has a certain uncertainty, we're still working and we're still trying to find the way to play with that huge, because there are 11 variables that has with 11 uncertainties, and trying to find the better solution in an 11th dimensions space with uncertainty is a mathematical problem that we have our colleagues that are mathematicians that are working on trying to solve that part. But if we just account that the RBs are almost equal, and this is more or less true within 1,000, and we consider the RC are equal and quite small, around 1,000 times smaller than RBs, that is also true for that system, we can perfectly arrive to a value that is around the G2, no? The thermal conductance of the central parameter. The G2 was the thermal conductance of the nanowire between beam 2 and beam 3 was around 45.5 nanowatts per Kelvin. And the uncertainty was slightly smaller than 10%. Something that is good, because as I said before, the final uncertainty on the thermal conductivity will be essentially driven by the determination of the area, by the determination of the diameter of the wire. And we got with a method that was able to determine the thermal conductivity of the nanowire without taking into account resistance, the contact resistance, and with a precision in the measurement, in the determination of the thermal conductance, better than the uncertainty that we will introduce on the measurement of the thermal conductivity through the geometrical parameters. And saying that, I can finish. I think I last a bit longer than 30 minutes, but I wanted to say that we were able to fabricate a multi-wire structure with to measure thermal conductivity of nanowires under the four-proof method. That the analysis and the uncertainties has driven to the design of the structures, permitting to theoretically minimize the uncertainty of the thermal conductance measurements below 10%, keeping it around the uncertainty in determining the thermal conductivity, that is driven by the geometrical parameters. By the measurement of the diameter. And I wanted to say that reduction of the uncertainty has been, how to say, potentiated by the use of the AC measurements that has improved the temperature determination and has permitted to experimentally achieve the theoretical Johnson-Noy limit in most of the measurements. Nowadays, and this is future work, I would say that we are solving the system equations with uncertainty to get more precise values, even though I could say that the values that we are, showing are quite, I'm quite confident of them. But we are using, variational methods. We are exploring the phases in the 11th dimension space, in order to find this point in between the different paraboles that will give us the perfect solution. But we have our colleagues from ATH that are working and we are already doing some measurements on the zinc oxide ALD thin films in order to determine the contribution on the nanowires. In order to do that, we are using the Bockley method that has a huge sensitivity of around, this is a combined sensitivity of around 1 nanowatt per meter Kelvin. More or less, that is, it's 1 watt per meter Kelvin per nanowatt of sample, per nanometer of sample. I want it could be better if I would put the resolution here. Now that is 1 watt per meter Kelvin per nanometer of sample. It means that if we have 1 nanometer of sample, we are able to determine the thermal conductivity of a sample that has 1 nanowatt of thermal conductivity. Okay, and that's all. This is all the acknowledgement I wanted to expect. I did not forget any one of the funding supports, financial supports, but this is everything. And if you have any question, I will be happy to answer.
Thank you very much, Aitor, for your very interesting and detailed talk. Thank you very much. So we have time for questions from the audience. Don't be shy. Okay, we have one. Cedric, please.
Yes, hello. Thanks for the talk. You mentioned at the beginning of your talk that it was important that your wires were porous, right? You said, yeah. I didn't understand why that was important. And also, as an outsider, I would also be interested in knowing a bit what the porous structure of your wire is.
Okay, maybe about the porous structure, maybe Luca and Eleonora could answer better. Why it is important to have a porous structure? Essentially because the mean-free path of the phonons is essentially a kind of a scattering point for the mean-free path of the phonons. These nanowires and the nanowires that we show in the article. I go to the presentation, and in this article, it was very close to the amorphous limit in that wires. Now, the thermal conductivity that we got, it was really close to the amorphous limit, and that was essentially because all the porous structure was acting as a scattering for the phonons, for the main phonons that used to drive heat on silicon. I don't know if I answered your question.
Yes.
And about the structure, this is like, let me, maybe Leonora and Luca could correct me, but this is like a tree structure. No? We have a porous structure that is going inside of the nanowires. This essentially arise because of as soon as we are doing the method and the metallic assisted etching, we have some little impurities of gold that they remain on the facets of the wire, and then they go inside and they do the but
Yeah, yeah.
there's not to be expert on that. Luca could
Yeah,
perfectly
sure.
correct.
It resulted initially from your thermal measurements, because we were not going into deep on the pore morphology of these wires, and from the thermal measurements and from the interpretation of the measurement and from the model from UAB group, it resulted also with the theoretical group from Riccardo Orali. It resulted that also that it was not so easy to explain the transport with only with a homogeneous porous structure. So there was something related to the morphology. So we did some SEM and TEM analysis, and also TEM tomography, and we discovered that there are some pores going longitudinally in the structure, but also there are some pores from the wall of the wires that are connecting to these main wires along the this pore along the wire. So it's a sort of a Christmas tree in which you have some holes that from the radial from the wall of the wires are entering and also forming a longitudinal structure. So
I tried to sketch it right here.
Yeah, this could be was explaining much better the behavior, and this was resulting from the TM analysis essentially. Let's say surely respect to a silicon nanowires of 100 nanometer, we have a very much lower thermal conductivity, because the material is not, it's crystalline but it's porous. So the confinement is in some way stopping the phonon propagation, because in the mean free path of room temperature of the in silicon is around 40 nanometers. So this is also literature from
most of it could be explained by boundary scattering.
Yeah. And but it's the system is also interesting because it offers the possibility to introduce other materials and having homogeneous materials, and in some way working on the thermoelectrical side of the measurement. Another comment I wanted to do is that these kind of measurements and fabrication are really time expensive, and we put a huge effort in the year in the last years in doing this, because you have to, we can create easily billions of nanowires, but you have to take one and putting on a structure that has been completely engineered, so has been planned and then realized to be able to suspend the wires and heating from one side and measuring from the other. So it's a very difficult work, but we need it. We need it because now it's plenty of, for example, scanning probe microscopy there is capable to see the thermal effusivity, the STHM. But this is not thermal conductive. It's not thermal conductance. It's just effusivity. So they're giving a map, and these SPM are not so quantitative because we are lacking of standards. And this is the metrological part of me that is speaking. But we really need standards for this kind of materials. So there is not so much work. There are not so many groups capable to investigate.
We lose.
We cannot hear Luca anymore. No.
You're frozen, Luca. I don't know what happened to your connection.
I don't know.
You're
Can you hear
back.
me?
We're back.
Yes.
I can switch off the camera. In any case, it's very important because we need to be quantitative with nano objects like nanowires, and it's not so easy to manipulate these objects. So it's very important also by the point of view of the standardization of materials, of new materials. So we keep on going on this.
Yes.
Okay, thanks. That was a very, very detailed answer to perhaps a stupid question. Yeah, thank you.
Not so stupid.
So maybe I can follow on Cedric's question. Thank you, by the way, Ettore, for this great presentation. It's very interesting. A bit far away from my field of expertise, but I am on the material point of view. Maybe going back to this pore structure. Do you think, or Luca and Eleonora, that you could play with this structure and the pore diameter, for instance, not only the organization, but Luca, you mentioned the possibility of filling the pores with other components to control the properties. That's the first question. Would that pore diameter has an influence of the performance of your system? And the second is, what about the mechanical stability of these coated wires to be then involved in the device? Is it a problem or not at all?
I think Eleonora can answer.
So regarding the mechanical stability, you mean the mechanical stability of the film of zinc oxide, or of the wire itself?
Of the coated wires.
So let's say that the wire are quite delicate during the process that actually my colleague Matteo Fretto is doing of taking one single nanowire and placing on this platform that UAB is developing. They can break due to stress that the nano manipulator is inserting on the nanowire, and we have not explored the mechanical stability or any difference between the pristine nanowires or the coated nanowires. Currently, we are doing with CLT in Grenoble TEM tomography of the infiltrated nanowires. So the nanowires coated with the zinc oxide to understand how much of the zinc oxide is actually gone inside the pore and what is actually coating outside of the nanowires. So we have not really a measure of any mechanical parameter. We have simply some of the measurements that were done on the roughness of the nanowires, so to establish how these nanowires are actually rough on the outside. But the measurement of the porosity can only be done with at least in my knowledge, with the TEM tomography. At least the imaging, actually, the imaging can only be done with TEM tomography. And I cannot recall your first question.
Pores.
Sorry.
The pore
It was
diameter.
the influence. If you could envisage the influence of the pore diameter, if there is any, it's pretty much the same approach that I was talking about mechanical stability, because at some point, also if you change the pore diameter, you can fragilize the system maybe, and when you use it, if you have some broken part or open porosity, maybe you lose some contact. I'm not sure. This is pretty related. And the question is there a structure that would be optimized for the performance of the system?
So I think for sure there is a percolation path inside the nanowire. As Aitor was mentioning, there is the mean free path is reduced inside the nanowire. due to the presence of the pores. We have not so much played with different porosity content, so we have used in this case N plus doped silicon as a starting point, and we know that as compared to low doped silicon, it gives higher porosity in the nanostructures, but we have only modified the actual diameter of the whole nanowire. So in this slide that Aitor is showing, so here the thermal conductivity was measured against nanowires with different diameter. So there is actually a change of a dependence of the thermal conductivity with respect to the diameter. For instance, there is, in this same article, if I remember correctly, there is another graph that shows how it is not dependent on the length, for instance, of the nanowires.
Sure.
Yeah, to complete the response, silicon is a very good mechanical material, okay? Porosilicon scales with the cube of porosity. So all the porosilicon is quite delicate, but at the same time, with nanowires, you can keep a very high aspect ratio. And the metal-assisted etching is the only type of etching giving you aspect ratio over 200. Okay. There is no deep reactive ion etching that is capable to do this. So we are doing, for example, this wire. We could have 50 nanometers of diameter for 75 microns. Okay, so the problem is that if you have an array, the array collapses because this is done in liquid, and so if you don't if you're not apply supercritical drying or other kind of drying, all the wires are sticking together. So there are some dimensions, but what is nice is that with the nanosphere lithography and metal-assisted etching, you can play with the dimensions. So you can have also nanospheres of 2 microns, for example. So we wanted to be close to the phonon confinement, so with 100 nanometer diameter. But in principle, you can do arrays of pillars of 500 nanometers, 1 micron, and for other kind of application, I think the bio, for example, it's possible to plan different structures with a different mechanical stability. And at this point, you can also play with the pores, because you can oxidize and remove in vapor environment without having condensation effects. And so in principle, you can also play with the porosity. I don't recommend to do it on the 100 nanometer wise, because it's very difficult. Mm-hmm. But you can work on pillars of 1 micron. And at this point, with a thermal oxidation, you can in some way enlarge the pores for sure.
Okay. Thanks a lot.
Question.
Thanks a lot for your replies.
There is one last question from Jonas. Mm-hmm. And then I think we are above time. Thank you. Jonas, please.
Thank you, Eleonora. Thank you also for fine presentation. I'm impressed of your nano scales, nano results. Actually, as for thermoelectrical application, the figure of merit depends also on electrical conductivity, and it's directly proportional. So the narrower your is nanowire, the lower is electrical conductivity. So is your system possible to be used for electrical conductivity measurements for probe system?
Well, that one can be used. We have to do some little modifications, but it could be used. But for electrical measurements, I think with Luca has already done measurements on substrates, on solid substrates, I would say. The point is we are in the process of doing a system that we should permit us to heat up and to do the full measurement of the nanowire, heating up and measuring the thermal conductivity and do the full setting measurement on the same wire. But Luca has been doing measurements of nanowires already.
Yes, what we're keeping to maintain is the capability to measure electrical conductivity of single nanowires of different types. We did something on copper oxide, other kind of materials, and but there is no need to suspend the wires. We are using a thick oxide, 500 micrometers of oxides, and with the nano manipulation and electron beam lithography contacts, we can do 4-point contacts. Sure. Yeah, the idea of zinc oxide infiltration is also to increase the electrical conductivity.
Yeah. Alfred has mentioned this.
Okay,
Yeah, that's right.
Yeah.
Thank you.
Well,
since you are here, if there are no questions, please give a look to the chat, to the link I put for the Netpore winter workshop that will be held on the 26th of February in Clavière on the border with France. It's close to Torino. There are some places left if you want to participate. There will be a number of prominent speakers like Frederico, Giuseppe Panicaro, Jarno Salonen from Finland, and others. And there are some places the prices are very low, so we wait for you. Keep in mind, give a look to the website, and if you are interested, see you there.
And we can promise a very friendly atmosphere because this is organized by Luca. So it will be fun.
Yeah, it's a cabin. It's a refuge on the ski tracks. We hope to have snow. We are waiting more snow, but it's nice in any case because the environment is small. We have something like 40 places, no more, and so speakers can stay together with the participants.
Yeah, thanks, Luca, for this information.
Thank you.
Another information I take advantage of here is to take also about the webinar. Any of you participant registered at Netpore can volunteer to give a talk on what you do in your lab and to introduce your research to others, because this is one of the greatest way to make new contact, and just tell us about what you are doing every day. So everyone is invited to volunteer for the webinars. We always have a space for you. Please don't hesitate. Don't feel shy. Everything is interesting. And every Thursday of the webinars is a good day because we learn many, many great things like today. So thank you again, Aiton, for this great talk.
Yes, thank you very much, Aitor. And we meet in the next webinar on the second Thursday of March.
bye-bye.
Thank you.
Have a great day.
Have a good day.
Bye-bye.
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 Bye. Thank you.